Okay, so in this video, let's actually go through the derivation for the naive Bayes classification algorithm, and it's we'll be taking the probabilistic approach in this derivation. All right, I explain everything step by step. So let's start. So let's say we have a data set with features uh, x1, x2, all the way to xn. Okay, these are the features, and I'm just going to write it as x because I don't want to write x1, x2 till xn every time. So I'm just going to take this as x. And let's say for this classification problem, I have k classes. All right. And k is 1 to k something. Yeah. So now basically in this problem, I need to find out to what class do all of my features belong, right? So I can pose this as a and if I have to write this mathematically, I can write it as probability that the class is ck given that our features are x. All right, and I can write this as p of x given ck into p of ck whole upon p of x. All right, this is Bayes theorem. So naive Bayes actually comes from the name comes from the Bayes theorem, Bayes for the Bayes theorem, and naive because we make an assumption, a very naive assumption that all the features are independent of one another. We will see how this is. Um, we'll see how this is applied in the derivation in a short while. So I hope everyone understood this because this is the important part here. I'm just expanding this using the Bayes theorem uh, into this, right? And this is just the probability that given my data set X, it belongs to some class Ck, where k equals 1 to k. Okay, so what I'm going to do now is I'm going to write this a little differently. I'm going to write this as probability of Ck given X equals probability of X given Ck x and ck. So what I'm going to do is I'm going to expand this using the conditional probability formula. P of x given ck can be written as P of x and ck, right? And ck whole upon P of ck. This I've just expanded this with the conditional probability formula. I've covered in one of the previous videos, so if you don't know that, just check it out. Into P of ck whole upon P of x. So this cancels out and we are ultimately left with P of x and ck whole upon P of x, right? So now if you look at this, I can say that regardless of what class I'm trying to find for my features, it can be P of c1 given x. This will be equal to P of x and c1 whole upon P of x, right? If it's some class C2, then I can write P of C2 given x equal to P of x and C2 whole upon P of x, right? And similarly, if it's something like P of CK given x, that will be equal to P of x and CK upon P of x. So you can see that P of x is a common denominator here, right? It's common everywhere. So I can eventually write this as P of CK because see P of X is there in each one of these each one of these formulations for finding the probability in the classes. So I can write this as P of CK given X is directly proportional to P of X and CK. All right. This is important to carry out the derivation forward. Okay, so now what I'm going to do is I'm going to write this P of Ck given x is equal to P of x and Ck, right? what I'm going to do is I'm just going to open the x up. I'm going to write cx1 and x2 all the way to and xn and ck. I can do that, right? Because these are just features in my data set. So x is nothing but the intersection of all the features together. Now comes the part where I'm going to assume the reason why naive Bayes is called naive is because we assume that all the features x1, x2, xn are conditionally independent of one another. What does independence mean? That if P of A given B and A and B are two events which are independent of one another, then P of A given B will be equal to P of A. All right? That is what independence is. So look, so I have this formula and I can write this as P of x1 conditioned P of x1 given x2 and x3 and xn and ck into P of x2 and x3 all the way to xn and ck, right? Look, if you just expand this, you'll get this part, you'll get this part in the denominator, and that denominator cancels out with this over here, and you ultimately you'll be left with just this part. So that's all I've done. I've just expanded it. I've tried to change it a little bit to finally arrive at the formula. So I can continue writing this as P of x1 given x2 all the way to xn and ck into P of x2 given x3 all the way to ck into P of x3 given x4 all the way to ck. This is intersection. Ultimately, I'll arrive at P of xn given ck. Okay? Ultimately, I'm going to arrive at this. Now, using the formulation of independence, conditional independence, that P of A given B is equal to P of A. If A and B are two events and they are independent of one another, I can write this as P of x1 given ck into P of x2 given ck. Because look, all the features are independent of one another, but the features are not independent of ck. So ck stays over here. Okay, ck stays, but all of these other features, x2, x3, x4, x5, they all go away. P of x3 into ck given ck all the way to P of xn given ck, right? This can be expanded as follows. In the end, I'll also have P of ck. Okay, because yeah, I'll also have P of ck. So what I'm left with now is basically I can write this finally as P of ck given x is proportional to P of ck pi. Pi is for multiplication, okay? I equals 1 to n xi given ck, okay? And then once I've written it this way, I can change this to P of ck given x is equal to 1 by z, because this was proportional here, right? You remember I took the P of x out from the denominator. If you go up here, I said that I can take, since these are all equal, since P of x appears everywhere in all of them, I can take it out and I can write P of ck is P of ck given x is proportional to P of x and ck, right? That's what I said. So to account for that proportionality, I'm bringing 1 by z back over here. 1 by z is nothing but z is nothing but P of x, okay? This is nothing but P of x. So I can write this as 1 by z P of ck into pi I equals 1 to n xi given ck. Okay, that is our formulation mathematical formulation for the knife Bayes classification algorithm. Now, I've taken this entire derivation from Wikipedia. I'll put the link for the Wikipedia uh, article in the description. Also, I'll put a link of this website called Shatterblog, where they actually tell you how the knife Bayes works practically. Everything that we derived over here, they applied practically to a problem, to a small data set, and they explain how knife Bayes actually works. I highly, highly recommend that you visit that blog. Just read through it. If you've understood this derivation, you will understand that application, the practical application for knife Bayes in that problem as well. I highly recommend that you go through it. If you've understood the derivation and you go through that example on Shatterblog, you'll understand knife Bayes in its entirety. And knife Bayes is also used as a baseline algorithm. It's a very trivial algorithm. It assumes that all the features are independent of one another. In reality, that might not be the case. Features are rarely independent of one another. So it's used as a baseline algorithm to it gives you some performance metric, and then it's used as a baseline algorithm. So you whenever you try to find a different algorithm to see if it works better or worse, you compare it to the knife Bayes baseline, all right? And it's also used heavily in spam detection of emails in text. So I'll stop the video here and I'll see you in the next one.